Okay, so as of right now, if a function fits either one of these tables right here, right? So if the function looks like anything like this or anything like this, we have integration techniques, right, to integrate these functions. Okay, so now let's take a look at some more advanced examples where what if the function doesn't look like anything on either one of these tables? What would we do? Okay, so let's take a look at this example right here. So first of all, we know that we don't want functions multiplying with each other, right? So we have this x squared plus 1 times this 5x. So as is, we know we cannot integrate this using any of the techniques that we know so far, right? But what we can do is, well, it looks like we can use some algebra to get this function to look the way we want it to look, right? So if I distribute this 5x in, I'm going to end up with 5x to the third plus 5x dx, and I can integrate this, right? I can integrate this right here because it looks like something from our integration tables. Okay, so right here we can use some algebra to get the problem to look the way we need it to look. So now if I needed to integrate this, I can. This would be 5x to the fourth power divided by 4 plus 5x squared, right, divided by 2, right, and then plus c. So this would be our integral right here, because we can use the integration techniques from the previous two tables, right? Let's take a look at another example. So this problem right here, so first of all, we don't want these functions dividing, right? We don't have any integration techniques when we have two functions being divided by each other. But similar to the last example, this example here, we can use some algebra techniques to get the problem to look the way we need to. So first of all, on top here, I can actually expand this out, right? If I expand this out, I'm going to end up with x to the fourth plus 2x squared plus 1 if I square this, right? And if I take this, change it to exponent form and move it to the top, I would end up with x to the negative 1/2. Now algebraically, I'm allowed to distribute this x to the negative 1/2 into this parentheses. This would give me x, and if I have the same base, I just add the exponents, right? So this would give me what, 3.5? So that'll be what, 7/2, all right, positive. All right, plus 2, this is 2 and a negative half, 3.5, x to the 3.5, and then plus x to the negative half, all right, dx, right? So we're integrating here. So basically, this original question, I cannot integrate it if it looks like this, all right? I don't have any integration techniques to integrate this if it looks like this. But using some algebra manipulation, right, I can get the problem to look like this, and I can integrate this, right? So now that the problem looks like this, I can integrate this using the techniques, right, from the two integration tables at the very beginning, okay? So if I want to, I can actually integrate this right now. I'm not going to, but I just want to make the point that from the very beginning, we can use some algebra techniques to make the problem, right, look like something that can be integrated, okay? Now let's take a look at another example. All right, right here. So this example right here, well, am I really going to expand this out 35 times? That's going to take quite a long time, right? So no one wants to do that. So this question here, first of all, we cannot integrate because we have this function being multiplied with this function, right? Like we don't want things being multiplied with each other, right? We don't have an integration technique for that. And then also, we cannot expand this, or at least we don't want to expand this out 35 times. That would take forever, right? So based on what we know so far, there's no way for us to integrate this right now. And we cannot use any algebra to get the problem to look like something that we can integrate, okay? So when this happens, all right, we have to use a method called U-Substitution, or integrating by substitution, all right? So we call this U-Sub for short, right? Integration by substitution, okay? So let's talk, this is similar to the last example, right? So we have x squared plus 1 to the 50th power times 2x. So first of all, you have this term being multiplied with this term, right? So we don't have any integration techniques for terms being multiplied with each other, right? Especially this one being raised to the 50th power. And we're not going to expand this out 50 times. That'll take forever, right? So we cannot use any algebra to manipulate this problem to make it look the way we want it to look, right? So that we can use the integration tables to integrate. So we have to use U-substitution. Now the first step in U-substitution is you need to choose something to be your U, right? Now in this example, we only have two options. We can make the U 2x or x squared plus 1. So here's a hint. Usually the thing that you want to make U is always going to be like inside of parentheses to some power, right? Like this. Or it might be like inside a radical, right? This might be what you want to make U. Or it might be like e to some exponent right here, right? Like 5x plus 1. You might want this to make U or something like that, right? So typically the main thing is usually it's always like a parentheses raised to some power, and it's the thing inside the parentheses. But like during a test or something, if you're not sure what to make U, just pick something and start working the problem out, and you'll see right away if everything cancels out nicely, then you know you chose the correct U, right? If you choose the wrong U, you're gonna notice that you get stuck right away, and then you know that, okay, I need to choose something else to be the U, okay? So in this example here, so x squared plus 1. Now, once you choose whatever you want to be the U, you're going to take the derivative of both sides. So this will give you du is equal to 2x dx, right? We're taking the derivative of both sides with respect to x. That's why we get this, right? Now, next thing, we're going to get the dx by itself. So we're going to get du over 2x is equal to dx, right? And then this is called substitution method, because now that we know dx equals this, I can substitute this instead of this dx over here, right? So when we do this, we're going to end up with, now when you're doing this work, it's very important. If you have not integrated, make sure you are still writing and showing this integration symbol, okay? Because that lets you know that, okay, I have not integrated. Now x squared plus 1, we made this our u. So this is u to the 50th power now, right? And then times 2x. Now instead of dx, we replaced it with du over 2x. Now, whenever you make this substitution, what's happened is you've made this problem in terms of u now. You're integrating with respect to u now. So what that means is you need all the x's to cancel out, right? And right here you see that, oh, it works out nicely. These x's are going to cancel out right here. So what we're left over with is just going to be, right, u to the 50th power, right, du. And this is something, this fits our integration table. This is a super easy integration, right? So here's something that's very important to remember. You cannot integrate until all the x's have canceled out, because this is in terms of du now. So the only thing you can have here is only the variable u. Okay, so remember that, that's very important. All the x's need to cancel out before you integrate, right? So now we integrate this. This is super easy integration. We get u to the 51st power divided by 51 plus c, and then you substitute back in your u. So u was x squared plus 1 to the 51st power divided by 51 plus c. And this would be your integral. Okay? Okay, let's take a look at another example here. All right, so first of all, when you're looking at this, the first thing you need to realize right away is you need to recognize when you need to use U-substitution, right? So if you don't have to use U-substitution, then don't. But this problem, right, can we make this problem look like something that fits the integration tables? We can't, right? Because, I mean, the only thing we can do is we can move this radical to the top, but we can't really distribute it or do anything, so, and we can't have these functions dividing. So we need U-substitution here because we cannot make this problem look like something, right, that belongs on those two integration tables. Okay, so something very important is you don't want to use U-substitution unless you have to, right? So the most important thing is you have to recognize when you need to use it or for which types of problem. Okay, so this problem we need U-substitution. So like I said, the first step is you need to pick something or to be your U, right? So your U, right, you can either make it cosine or this root, all right, x. So this root x, typically, usually I would try something with the root x right here, right? But like I said before, if you're not sure what you should make your u, just try something, and then you'll see if things cancel and work out nicely or not. If it doesn't, try something else for your u, okay? So if I make this root x, so this is the same thing as x to the half power, right? If I take the derivative of both sides with respect to x, I'll end up with du, right, is equal to, this is going to give me 1/2 x to the negative half dx. So basically I have du is equal to 1/2 square root x dx. Now I want to get the dx by itself, so I multiply by 2 root x on both sides. So I get 2 root x du is equal to dx. So now that the dx is by itself, I know that it equals this, and I can substitute it right here. Okay? Now, when I rewrite this, this is cosine. Now remember, our u was x to the half power, which is the same thing as root x. So I have cosine u now over, now I'll keep this root x right here, and then instead of dx, I replace it with this, 2 root x du, 2 root x du. Now what happens, all right, remember, what do we want to happen? We want the stuff with the x's to cancel out. This cancels out this. Now remember, any constant, we can pull it out in front of the integral, all right, symbol. So I'm going to take out this 2 here because this is just a constant multiplying with this. I'm going to pull this out to the front, 2, and then we're integrating just what now? Cosine u du. All right. Now remember, everything should be in terms of u, which it is. This fits our integration table, all right, from the beginning. We can integrate this very easily, right? So if we integrate this, we're going to end up with 2. All right. If we integrate cosine, we're going to end up with sine. All right, the u, just keep it the same, and then we're going to have plus c. And then substitute back in the u. So we're going to get 2 sine square root x plus c. This will be our integral right here after we've integrated, right? Okay, so let's take a look at another example here, right? So first of all, we need to recognize when we see something like this, like, okay, can we make this fit the integration table? So we have this 2x to the third, treat this as one single function, is multiplying with this sine x to the fourth. So we can't do any sort of algebra manipulation, and we cannot have these two functions multiplying with each other, right? So basically what we're going to do is we're going to use U-Substitution. We need to make something our u, right? So usually this angle here that's inside this parentheses, all right, I'm going to make this my u, x to the fourth, right? And then I take the derivative of both sides. I get du is equal to 4x to the third, right, dx. So get the dx by itself. I get 4x to the third, right, on the bottom here is equal to dx. And then we can do our substitution. So if I substitute now, this is still 2x to the third. We have sine, right? This is u now, right? And then we have du over 4x to the third. Now remember, what do we want to happen? We want all the x's to cancel out. So these x's cancel, perfect. When that happens, that means you pick the correct u. The 2 and the 4 can simplify, so this will be a 2 here. So now you notice this 2 is on the bottom, so that means this is like 1/2. So what I can pull out to the front of the integral symbol, right, is 1/2. So we have 1/2. We're integrating sine u du. And then this fits our integration, our table. So we have the 1/2 here. All right, if we integrate sine, that's going to give us negative cosine, right? Negative cosine. Right, we have the u, and then plus c. So basically this is going to be negative 1/2. All right, cosine, substitute back in the u, our u is x to the fourth, plus c. Okay? Okay, so let's take a look at the next example here. So first of all, we have these two functions being divided, And we cannot algebraically manipulate this to make this problem look like anything on the integration table. So we know this needs U-substitution. So we're going to make our U. Right, now typically, remember I told you, you want to try and make the U something inside like a radical. So I'm going to make it this 2x squared minus 8x plus 1. I take the derivative, all right, on both sides. I'm going to get du is equal to, the derivative of this would be 4x minus 8 dx. So get the dx by itself, so I get du over 4x minus 8 is equal to dx. Now I'm going to substitute. All right, dx equals this, so I'm going to substitute it here. So now I'm integrating the 2 minus x here, 2 minus x. Now on the bottom here, remember this is going to become basically root u, right? So the square root of u, because I made this whole thing inside here u. And instead of dx, I have du over 4x minus 8. So this problem is a little bit tricky because you might say, about like, wait, I'm stuck. I can't do anything, right? I need the x's to cancel out. But what you should recognize here is, wait, well, if I factor out a negative 4, what's going to happen is this x will become negative, right? This will become a positive 2, right? So then now this is negative x plus 2, which is the same thing as up here, 2 minus x. These are the same now. So then we can get these to divide out, right? And then we have this negative 4 on the bottom, right? It's in the denominator. So what I can pull out outside of the integral would be a negative 1/4, right? And then this problem here, I have this u, right? Square root u on the bottom. I'll just move it to the top. That's u to the negative half, right? du. Okay? So now this fits our integration table. This is a super easy integral. This is just going to be negative 1/4 times, we add 1 to this. So that's going to give us u to the positive, all right, half, right? Divided by half is the same thing as multiplying by 2. And then we have plus c. So if we simplify a little bit, we're going to end up with negative 1/2. U is going to be 2x squared minus 8x plus 1 to the half, right? You could change this back to a radical if you want. That's fine. Plus c. And then this would be your answer right here. Okay? Okay, let's take a look at another example here. All right. So first of all, we have to think of this as a 2x times this e to the x squared, right? So it kind of looks like a product rule, right? So we don't have anything, we cannot integrate anything that looks like a product rule, right? Two functions being multiplied with each other. And there's nothing to, all right, do to this algebraically where we can manipulate it to look like something on the integration table. So we need to use U-substitution, okay? So U-substitution, so you have to decide what should I make my U, okay? So now, like I said before, if you're not sure, just try something. Let's say, for example, here, I want to make the u 2x. What would happen? So if I make the u 2x, right, and I take the derivative of both sides, I would get du, right, is equal to 2 dx. So du over 2 would equal dx. So when I do this substitution, though, well, what's going to happen? I'll end up with 2x e to the x squared, and then we have du over 2. Now what happens, okay, these 2's cancel, but I'm still left with x's. If you still have x's left over and there's nothing else you can cancel or divide out or anything, and you're stuck with x's still, that means you chose the wrong u, okay? So I'm showing you an example here of what happens when you choose the wrong thing to be u. What happens is you're going to get stuck with x's still left over, okay? So when you have x's still left over, that means that you've chosen the wrong u. You need to try something else to be your u, okay? So in this case here, so what am I going to try to be the u? All right, u here, I'm going to make it this x squared, the exponent of this right here. Now, du is going to equal 2x dx, so du over 2x is going to equal dx, right? Now I can do the substitution. So I'm integrating. I have 2x e to the u power, right? and then we have dx, all right, is going to be replaced with du over 2x. Now you notice this fits perfectly. The 2x's both divide each other out, and I'm integrating e to the u power du, right? So remember, e to any power, when you integrate it, it's just going to give you the exact same thing. So when I integrate this, this will still be e to the u plus c. So then my answer is going to be e to the x squared, right, plus c. Okay? Okay, let's take a look at this next example here. Now this example here is going to be really, really tricky. Okay? So first thing is you see that, well, it's just cosine to the third power, right? So cosine, all right, cubed x dx. So what are we going to do here, right? So the first thing is you might think, well, I can always split this up. This right here, I can think of this as cosine squared x times another cosine x dx, right? Now, let's say you get this far and you're like, okay, well, if I make my u cosine x, if I take the derivative of this, I'll get du is equal to, I'm going to end up with the derivative of cosine is negative sine x, and then we have dx. So my du over negative sine x, right, is equal to dx. Now, if I substitute this in here, though, you notice that, well, it's not going to even get rid of this cosine x right here, right? It's like if I substitute this right here into here, well, the cosine x is still going to be here. This cosine squared x is still here. I still have a negative sine x now. So it doesn't help me, right? So you're kind of stuck. So what do I do? All right, I'm trying cosine. I make cosine my u. I don't see anything else. So what do I do? So here's where you have to kind of think, well, cosine squared is also the same thing as what? You have to remember your identities. This is the same thing as 1 minus sine squared x. Now, instead of making my u cosine, right, I can think of this as, well, I can make my u sine now, sine x. So when I take the derivative here, I'll get du is equal to, what's the derivative of sine x? Cosine x dx. Get the dx by itself. So du divided by cosine x is equal to dx. Now if I make this substitution, it looks like it's going to help me, right? I substitute it right here. This is going to give me 1 minus. Now remember, our u is sine x. So this is going to become u squared now. You see how this fits our integration table. And then we have times cosine x, and then instead of dx, we have du over cosine x. And we see that these cosines are going to cancel each other, which is what we want. We got rid of everything that has an x. So now this is just going to give us, right here, this problem we have, we're going to integrate 1 minus u squared du. And this fits our integration table. We can integrate this, right? So if we integrate 1, it's just going to be u, right? And then minus, if we integrate this, this would be u to the third. We add 1, divide by the new exponent, plus c. And then we substitute back our u, which was sine x. So our answer is going to be sine x minus sine, all right, cube x divided by 3 plus c. Okay? So that one was a little bit tricky. All right, so let's take a look at one last example here. All right, so first of all, we get this problem. So you have to recognize that, okay, I don't want functions dividing each other. I don't have an integration technique for that, right? And I cannot manipulate this in any way to make it fit the integration table. So we know that we need to use U-substitution. So what should I make my U, right? So once again, like I've told you before, so let's say you're not sure what to make your U. Just choose something and then just start doing the work. So let's say I think the u should be 2x minus 3. So if you make it 2x minus 3, so if you take the derivative, you would get du is equal to 2 times dx. So du over 2 is equal to dx. But if we make this substitution now, you would end up with, right, u over x squared minus 3x, and then the dx all right, we substitute with du over 2. So you notice this doesn't help you, right? So when the x's don't cancel out and you're still left with x's, that means you've probably chose the wrong u, okay? So this doesn't help you. So unfortunately, you have to redo the problem and choose something else for your u, okay? So whenever that happens, that means you chose the wrong thing to be u, okay? Now, so if I make the u x squared minus 3x, if I take the derivative of both sides, I get du is equal to 2x minus 3 dx. Get the dx by itself, so du over 2x minus 3 is equal to dx. Now we can substitute, so we have 2x minus 3 on top. On the bottom, remember this is our u now. And then we have, instead of dx, we substitute, we get du over 2x minus 3. Perfect. I see these are going to cancel out. If I move this u to the top, right, I'm integrating, right, u to the negative 1 power du. So you have to remember, like, I can't add 1 to this and divide, because then I'll be dividing by 0. So this was that special case where we have to remember, oh, we use natural logs. So when we integrate this, it's actually going to be the natural log, right, of absolute value u, right, absolute value u plus c. So just substitute in the u, which is x squared minus 3x plus c, and then this is your answer. Okay.